Assalamualaikum warahmatullahi wabarakatuh and a very good day. So my name is Najihah binti JAMALUDIN and I will start presenting the atmospheric dispersion modeling chapter. So we will start with the introduction part. So what is actually the air dispersion modeling, or we can call as ADMS? It's actually the advanced dispersion model to calculate the concentration of pollutants emitted from continuously from point, line, volume, and area sources. So what it need to be calculated or determined to make sure that the concentration of the pollutants that emit its compliance with the National Ambient Air Quality Standards or in AAQS. So next, I will explain on the physical explanation for the dispersion. So the mechanism of the dispersion is say that it will continuously release the pollutants into a steady wind and initiate the process that have plumb rise, bends over and travels with mean wind. And in AD formation, or called as swirl in air, it happened because of the heat or wind blowing over bumpy things, and it will mix the pollutants with the clean air and it will spread it around. And the thermal this, of course, when we say about the thermal, is related to the temperature, where the sun will warm the ground and make the pollutants swirl in air and mix it with the clean air. And figure beside here is actually the horizontal and vertical spread, where it shows that the pollutants disperse both horizontal and vertical from the plumb center line. Next, physical explanation for the dispersion are influenced by the solar insolation and wind strength, as the solar is actually affect the thermal, and stronger wind will generate and contribute to the dispersion. Next, the time averaging and wind fluctuation, where the pollutants concentration is over time. Consider uh, consider that the wind fluctuates and it can change the direction, and intensity leads to the larger downwind area. And last but not least, the Gaussian dispersion equation is considered that the statistical nature of dispersion, and the model we will discuss in the next slides. So this is the equation in Gaussian model, or we call as normal distribution, and the equation is for the dispersion of the non-reactive gas pollutants from the sources. So there are two equations here, which is the 20.2a and 20.2b, where it is actually the correction for realistic modeling, and it is for infinite dispersion underground, and both equation summation. We can get the equation in the previous slide. And next is the reflection at ground level, is the model that assume the plumb reflection at ground level, and the behavior will show in the slide after this. So this is the schematic diagram in the Gaussian model, where the A is actually the mathematical dispersion of pollutants underground, and B is the figure for the reflection due to an image source. Next, we will go for the atmospheric stability classes, and this is from the Pasquier-Gifford method, and we can see that from the horizontal dispersion coefficient and vertical dispersion coefficients, as the function of downwind distance from the source, that A is the most stable from both coefficient. So next, this is the stability classification based on the factors such as the surface wind speed, the incoming solar radiation during the daytime, and cloudiness during the nighttime. And surface wind is a speed is measured at 10 meters above the ground, and we have 6 classes A, B, C, D, E, F, where the class A is very unstable, and regardless of any wind speed, when it is overcast condition, it's either day or night, we can assume is in class D. Next, this is one of the example in the book to calculate the ground level concentration and using the Gaussian model equation and the coefficient graph. So the equation given the wind speed, and it stated that the condition is overcast morning, so we can assume that it is in class D. And from the equation 20.3 and 20.4, we can get the coefficient y and coefficient z, and we can substitute in the equation 20.1 for the Gaussian model equation, and we can get the ground level centerline concentration 2 km downwind from the stack, and we get 159 microgram per cubic meter. And the B is to calculate the concentration at 100 meter of the centerline at the same x distance. So we can substitute to the equation, and we can get 116 microgram per cubic meter. Next, the dependence of concentration on averaging time. So this is the equation for the concentration of two averaging time. Next, the maximum downwind ground level concentration is always occur on the center line. So both Cmax and Xmax depends on the effective stack height and wind speed. So next, the downwind concentration under an elevated inversion. So the downwind concentration under elevated inversion is acts like a lead, where it hindering the output dispersion of pollutants, just like the figure 20.11. The inversion layer reflects the pollutants. Similarly to the ground, consideration of multiple reflecting surfaces. And the equation 20.7 is actually equation for the trap lump under an elevated inversion. Consider the reflecting surfaces, and it involves the height from the ground of the inversion layer L and this summation index. So next is the still in downwind concentration under an elevated inversion. So the box model for dispersion is actually derived from the mass balance, aligning the box length with the wind direction and assuming the complete sync within the box. And the box height and width are determined by physical factors. The outlet concentration C is given in the equation 20.10. So next, we will go for the design consideration for the stack, and why we need to have stack design. So to make sure that we're able to specify a stack that is tall enough to release the pollutants under all meteorological conditions. So the basic procedure for the stack design. The first one is we need to analyze the meteorology, make a preliminary hazard assessment based on meteorology, test various cases of physical stack parameters, height and diameter, plumb-rise models and plant location, and consider effects of the local terrain and review the results. And either the tall stacks and plumb-rise is make sense or not. And next is the plumb-rise. So the plumb-rise is actually, this is the plumb-rise equation, and the modeling of the rise of a plumb emitted from the stack into a horizontal wind involve complex mathematical consideration. And the plumb rise, it actually depends on a few parameters such as temperature, molecular weight, and exit velocity of the gas. And besides that, the atmospheric parameters such as the wind speed, ambient temperature, stability condition also play a significant role to the plumb rise. Next is the critical wind speed. It is actually inversely proportional to pre-exponential term and wind speed. Maximum Cmax occur at U at critical wind speed, and balance of term exponential increases, pre-exponential decreases, and graphically represented as a curve peaking at critical wind speed. and it depends on atmospheric stability and plumb rise model, and best determined through the computer modeling for accuracy. Next, we will go for the other stat design consideration. So we have 8 other suggestions. The first one is structure creates low pressure zones and weight behind them. And when it's a large structure, it can disturb airflow and it can cause the plumb dam wash. And the turbulence from buildings can extend up to twice the building height. And next is stack height should be 2.5 times the highest nearby building to avoid any downwash. And to prevent the downwash, the stack diameter should ensure the exit velocity is more than 1.5 times wind speed. And next is mechanical adaptation like flat disc or wind turning vents counteract downwash effects. And last but not least is stack design consideration include cost implication due to increased gas velocity and pressure drop. Next, what is actually the computer program for dispersion modeling? So it is actually the mathematical representation of pollutants, dilution and dispersion in the open atmosphere. And at the layer of this topic, we know we calculate from the Gaussian model dispersion equation, and it is actually the commonly used, although it has own imperfections. And the dispersion parameters are determined empirically but come with inherent few limitations to the program, and widely used due to its simplicity, ease of understanding, and adaptability to computer programs. And computer programs yield answer with correct data input, but users should be cautious about the inherent assumption and limitation from the program. Next, the mobile sources and line sources model. Can see that we have 3 equations here: 20.25, 20.26, and 20.27. And the mobile sources actually emits large amount of CO, NOS, and VOCs. And light duty vehicles are used as mobile sources and emits pollutants. And EPA computer program mobile sets used to calculate emission factors. 4K. Lastly, our last part is conclusion part. So what I can conclude from this topic is the first one is we learn about the atmospheric dispersion modeling, where it's actually the tools to understanding and to predict how pollutants move in the air. And the second one we learn about the Gaussian modeling equation, where it has its stability classes and consideration for averaging times provide a widely used framework from tall stacks to critical wind speeds and stack designs. Various factors impact the dispersion air. And last but not least, we learn about the computer program uh, in modeling, covering both points and line sources, and understanding the physical processes like plumb rise and ADs enhance our understanding about the dispersion mechanism, and we learn about the Gaussian models for short and simplified box model proof useful. That's all from me. Thank you.